Welcome to Episode 50, Google's Trusted Infrastructure and Encryption. In this discussion, we explore what makes Google Cloud's foundation secure by design rather than secure by reaction. The phrase trusted infrastructure describes the combination of hardware, software, and operational processes that protect customer data from the moment it is created until it is safely deleted. Trust is not assumed, it is earned through transparency, consistency, and verifiable controls. Google's model relies on defense in depth, meaning every layer of the environment reinforces the one beneath it. From chips to data centers, each component contributes to confidentiality, integrity, and availability. Understanding how these layers interlock helps leaders and practitioners appreciate why cloud security depends as much on architecture and governance as on tools and alerts. Trusted infrastructure begins with secure hardware roots and a controlled boot process. Each physical server includes a custom security chip that verifies the integrity of firmware and software before allowing the system to start. This root of trust ensures that only authorized code runs, preventing attackers from inserting malicious software at the lowest levels. Boot verification continues through each stage, confirming that the system matches its expected state. If tampering is detected, the device will not proceed until remediated. This approach creates an unbroken chain of trust from silicon to operating system. By anchoring security in hardware, Google ensures that even advanced threats cannot easily bypass foundational protections. Physical security complements these digital safeguards through rigorous control of every facility and device. Google's data centers are purpose-built with multiple security layers, including biometric access, surveillance, and round-the-clock monitoring. Only authorized personnel can enter, and their actions are logged and audited continuously. Hardware devices follow a defined life cycle, from procurement and inventory through maintenance and final destruction. When servers are decommissioned, storage media is securely wiped and physically destroyed, verified through documented procedures. This life cycle management ensures that no component leaves the environment without assurance that data remnants are irretrievably erased. Physical security forms the first visible barrier in a chain of trust that extends through every operational process. Isolation at every virtualization layer keeps workloads separate and protected from one another. In multi-tenant environments where customers share underlying infrastructure, isolation is essential. Google's hypervisor design creates strong boundaries between virtual machines, preventing cross-access even on the same hardware. Networking layers add further segmentation, controlling how traffic flows between systems and regions. At the storage level, logical separation ensures that data blocks belonging to one customer cannot be read by another. For example, when a compute node is reassigned, its memory and local storage are reinitialized before reuse. These layers of separation combine to provide customers with confidence that their workloads operate in private, secure spaces, even within shared physical resources. Production access controls ensure that human intervention in cloud systems remains rare, authorized, and traceable. Engineers who maintain the platform must follow strict approval workflows and multi-factor authentication before gaining access. Every access event is logged, reviewed, and correlated with a justifiable maintenance purpose. Automated systems perform most operational tasks, reducing the need for manual involvement. When intervention is required, access expires immediately after the task completes. These controls reflect a philosophy of least privilege at global scale. For customers, this means that no individual employee can arbitrarily view or modify data. Oversight mechanisms ensure accountability, and every administrative action leaves an auditable trail that reinforces trust in the cloud's operations. Software supply chain integrity has become a defining aspect of modern security. Google's internal build systems verify the source, dependencies, and cryptographic signatures of every component before it reaches production. This process ensures that only verified, untampered software enters the environment. Binary authorization enforces similar controls for workloads customers deploy themselves, requiring signed images before execution. These safeguards protect against the growing threat of supply chain compromise, where attackers target development pipelines rather than production systems. By securing code provenance from development to deployment, Google maintains confidence that the software running its infrastructure and its customers' applications is both authentic and trusted. Encryption by default for data at rest protects information even if physical or logical boundaries were somehow breached. All data written to persistent storage, including databases, disks, and backups, is automatically encrypted using strong algorithms. This process happens transparently, requiring no action from the user. Each piece of data is associated with unique encryption keys stored in secure key management systems. Even temporary data, such as logs or caches, receives the same protection. For customers, this means that data privacy does not depend on manual configuration. Encryption at rest is built into the infrastructure itself, turning confidentiality from an option into an inherent property of the system. Encryption in transit extends that protection to data moving across networks, both within Google's infrastructure and between regions or external endpoints. All internal communication between services is encrypted using secure protocols such as TLS, ensuring that even internal traffic cannot be intercepted or modified. When data leaves the cloud, it remains encrypted until it reaches an authorized destination. This consistency eliminates weak points often found in mixed environments. For instance, a workload in one region communicating with another through Google's backbone automatically benefits from end-to-end encryption without user configuration. The result is a seamless protection layer that follows the data wherever it travels. Customer-managed keys add an additional layer of control for organizations with specific governance requirements. Instead of relying solely on provider-managed encryption, customers can create and control their own keys through Cloud Key Management Service. They can rotate keys periodically, revoke them at will, and monitor usage through detailed logs. For example, a financial institution might maintain strict internal policies requiring that decryption capability always remains under its authority. Customer-managed keys provide this assurance while still benefiting from Google's operational resilience. The combination of provider encryption and customer key control balances convenience with sovereignty, allowing security teams to align encryption practices with their compliance mandates. Hardware Security Modules, or HSMs, further strengthen encryption key custody by storing keys in tamper-resistant hardware. These devices perform cryptographic operations securely within their boundaries, never exposing the keys themselves to external software. HSMs are certified to international security standards and undergo regular audits to verify integrity. Organizations can choose between Google-managed HSMs or externally connected ones, depending on their compliance needs. For example, a government agency might use its own HSM cluster integrated with Google Cloud for additional assurance. This hardware-based custody model ensures that cryptographic trust anchors remain physically and logically isolated from potential compromise. Envelope encryption adds another dimension of security through hierarchical key management. Instead of encrypting data directly with a single key, Google encrypts the data using one key and then encrypts that key with another, higher-level key. This layered model allows frequent rotation and fine-grained access control without re-encrypting massive data sets. Split key management further distributes control. One part remains with Google and another with the customer, so that no single entity can decrypt data alone. These designs balance usability, scalability, and privacy. Even within Google's trusted systems, encryption is never treated as a static safeguard, but as a dynamic, multi-tiered mechanism continually reinforced by policy and cryptography. Data deletion and sanitization are crucial to maintaining trust throughout the data lifecycle. When customers delete information, Google follows a verified, multi-step process that removes data from active systems, overwrites storage locations, and confirms completion through internal audits. Backup copies and replicas are also scheduled for deletion in accordance with policy. If hardware containing data is retired, it undergoes physical destruction verified by secure logging and photographic evidence. This rigor ensures that deleted data cannot reappear or be recovered by unauthorized parties. Proper deletion practices close the loop of confidentiality, proving that data stewardship continues even after information is no longer needed. Transparency reports and shared assurances bridge the gap between technical operations and customer confidence. Google regularly publishes audits, certifications, and reports detailing how its infrastructure meets international standards for privacy and security. Customers can review compliance mappings to frameworks like ISO 27001 or SOC 2 and request detailed evidence through trusted channels. Transparency also extends to incident response. Google discloses how it handles requests for data access from governments and other entities. These practices reinforce trust by aligning visibility with accountability. Security is not just built, it is demonstrated openly and continuously. Defense in depth remains the guiding philosophy that ties all of these mechanisms together. Google's trusted infrastructure is not a single product, but an ecosystem of interlocking controls, physical, technical, and procedural, that reinforce one another. Encryption, identity management, monitoring, and secure hardware form a self-checking system where no layer stands alone. For organizations building on this foundation, the lesson is clear. Lasting trust comes from design, not from afterthought. When every component is conceived with protection in mind, security becomes invisible yet omnipresent, allowing innovation to flourish safely within the boundaries of proven assurance. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.